Hi everyone, welcome to my channel. In this video, I'm going to explain some important formulas for the subject Basic Circuit Analysis for Unit 2 Single Phase AC Systems. The first one is a time period. So it is the time after which the same shape of waveform that repeats, or the time taken to complete one cycle is called time period. It is measured in seconds. For a DC, the time period will be infinity, whereas for AC, that is alternating waveforms, you have to calculate. The frequency, it is a number of cycles per second, is called as a frequency. It is represented with the F and units are hertz. Therefore, the formula for frequency is reciprocal of time period, therefore F is equal to 1 by T. Since time period for DC is infinity, therefore the frequency of DC is 0. And for AC is the frequency is 50 Hz for India. Next, the alternate current waveform that can be represented with a sinusoidal waveform. So it is given as V is equal to Vm sin omega t. So whereas the current waveform is nothing but I is equal to Im sin omega t plus or minus phi. So here the voltage V is taken as a reference waveform and the current is varying with respect to the current with respect to the voltage V. Here in the formula V is equal to Vm sin omega t. So small v, that is the starting small v, it is called as an instantaneous value. Whereas Vm, it is called as maximum or peak value. Omega is called as angular frequency, that is given as 2 pi f radians per second. So here with respect to current, here small I is called as instantaneous value of the current I, and Im is called as maximum or peak value of current. Omega is same angular frequency, whereas phi is called as a phase difference between voltage and current. So this phi is positive for the current leading the voltage, phi is negative for current lagging the voltage. Now the average value, so it is average of all the instants throughout the time period, it is called as average value. So for sine wave, the average value is 2 pi, its value that is nothing but 0.637, and for square wave, its value is 1, for triangular it is 0.5, for sawtooth also its value is 0.5. The average value formula can be given as V average is equal to 1 by T integration 0 to T small v dt. Next, RMS, root mean square value. So the formula is given here. Vrms is equal to root over 1 by T integration 0 to T V square dt. So for sine wave, so its value is 0.707, and triangular wave its value is 0.577. So for square wave its value is 1, for sawtooth its value is 0.577. So next, the form factor, it is a ratio of RMS value to the average value. So for sine wave its value is 1.11, for square wave its value is 1, for triangular waveform it is 1.155, and for sawtooth also its value is 1.155. Next, peak factor or crest factor, it is a ratio of peak value by RMS value. So for sine wave its value is root 2, that is 1.414, for square wave it is 1, for triangular and sawtooth waveform the value is same, that is root 3, 1.732. The calculation of these average value, RMS value, next form factor and peak factor are already covered in the previous videos. I gave the link in the description, so please go through it if you did not see that videos. So next term, impedance. So it is a sum of resistance plus reactance. Therefore, that is equal to R plus Jx, where R is called as resistance, X is called as reactance. So its value is R plus J into XL minus XC, where XL is called as inductive reactance. Its value is 2 pi FL, and XC is called as capacitive reactance. Its value is 1 by 2 pi FC. So the unit for resistance is ohms, unit for reactance is also ohms. Therefore, the unit for impedance is also ohms. Next, admittance. So it is a reciprocal of impedance is called as admittance. Therefore, Y is equal to G plus JB, where G is called as conductance, B is called as susceptance. So susceptance is given as BC minus BL, where BC is called as capacitive susceptance and BL is called as inductive susceptance. the values for BLE is 2 pi FC, the value for BCE is the value for BLE is 1 by 2 pi FL. Here these two will be interchanged. So here the value of BCE is 2 pi FC, the value of BLE is 1 by 2 pi FL. So BL is called as inductive susceptance, BC is called as capacitive susceptance. Therefore here the unit for conductance is mho, the unit for susceptance is also mho, therefore the unit for admittance is mho or Siemens. Now we will see some circuits with the pure resistance supplied with the AC. So AC with pure resistance here as shown in the figure. So here I gave the conclusions for these circuits. Here E is equal to Em sin omega t as input and I is equal to Im sin omega t is the output here. Upon observing these two, the phase difference is 0. Therefore, the power factor is cos phi, that's value is 1, and average power is given as P average is equal to Vrms Irms into cos phi, but cos phi is equal to 1, therefore average power is Vrms into Irms. The impedance of the circuit is only resistance because it is a pure resistive circuit. Therefore, for pure resistive circuit, current and voltage both are in phase. In phase means the phase difference is 0 degrees. Next, for pure inductive circuit, so if you apply E is equal to Em sin omega t, the output current is I is equal to Im sin omega t minus 90. That means if you take the E as a reference, voltage reference, if the voltage wave starts at omega t is equal to 0, the current wave starts after 90 degrees to the voltage wave has started. That means the current lags the voltage by 90 degrees. And the impedance of the circuit is Z is equal to J into XL, that is J 2 pi FL. The phase difference here is phi is equal to 90, therefore power factor is cos 90 0 and the average power also 0. That means pure inductive circuit does not consume any amount of power. Next, AC with pure capacitance, here E is equal to Em sin omega t as the input and the output is Im is equal to sin omega t plus 90. That means the voltage wave is started at omega t is equal to 0 degrees, whereas the current wave has already started previously at an angle of omega t is equal to minus 90 degrees. So for pure capacitive circuit, current leads the voltage by 90 degrees. So since the phase difference here it is 90 degrees, so cos phi is 0 and the average power is also 0. That means the pure capacitive circuit also does not consume any amount of active power. Next, AC with series RL. So here both resistance and inductance are connected in series with AC supply. So E is the input, I is equal to Em sin omega t and I is equal to Im sin omega t minus phi. Here the circuit consisting of both resistance and inductance. Therefore, the phase angle is not 90 degrees. It should be less than 90 degrees. So that is given by an angle of phi, where phi is nothing but tan inverse of XL by R. So the impedance of the circuit is Z is equal to R plus JXL. And for series RL circuit, current lags the voltage by phi, where the phi is nothing but tan inverse of XL by R. And the average power is Vrms into Irms cos phi. And the power factor is cos phi, where phi is the tan inverse of XL by R. Now AC with series RC, so if the voltage E is equal to Em sin omega t is applied, I is equal to Im sin omega t plus phi is the output. So here current leads the voltage by an angle of phi, that is not 90 for pure capacitance. Therefore, where phi is given as minus tan inverse of XC by R, and the power factor is given as cos phi. So cos of this angle phi is nothing but minus tan inverse of XC by R, and the average power is also given as Vrms into Irms cos phi, and the impedance of the circuit is Z is equal to R minus JXC. Next, AC with series RLC, so V is equal to Vm sin omega t is input, I is equal to Im sin omega t plus or minus phi here. So here where plus is for leading case, minus is for lagging case. So and the impedance is given as Z is equal to R plus J into XL minus XC, where the phase difference is given as phi is equal to tan inverse of XL minus XC by R. So the phase phi will be positive if the circuit behaves like inductive circuit, and phase phi becomes negative if the circuit behaves like a capacitive circuit. Therefore, cos phi is nothing but cosine of the phase angle phi, and the average power is given as Vrms Irms cos phi. So therefore, for series RLC circuit, if XL greater than XC, current lags the voltage by phi, and the circuit behaves like an inductive circuit, because inductive reactance will be dominant here. So similarly, if XL less than XC, current leads the voltage by phase angle phi, and the circuit behaves like a capacitive circuit. Now series AC with parallel RL circuit. So here E is the applied voltage. Since it is a parallel circuit, voltage will be same across all the elements, and the current is given as I is equal to V into Y, where Y is nothing but G minus JBL. Admittance Y is equal to G minus JBL, where G is nothing but 1 by reciprocal of resistance, and BL is nothing but 1 by omega L. And the phase difference is given as phi tan inverse of minus BL by G, and in terms of resistance and inductance, so phi is equal to tan inverse of minus R by omega L, and the power factor is called as cos phi, and the average power is Vrms Irms cos phi. For parallel RL circuit, current lags voltage by an angle of phi, where phi is nothing but tan inverse of minus BL by G. Now AC with parallel RC circuit, E is equal to Em sin omega t, and the current is I is equal to Vy, and the admittance phi is equal to G plus JBC, where G is nothing but 1 by R, BC is nothing but omega C, that is 2 pi FC, and the phase difference here it is tan inverse of BC by G. So in terms of resistance and capacitance, phi is equal to tan inverse of omega C R, and the power factor is cos phi, and the average power is Vrms Irms cos phi. So for parallel RC circuit, current leads voltage by phase phi. Next, AC with parallel RLC. So here all the three elements are in parallel RLC. Therefore, E is equal to Em sin omega t, I is equal to Vy. So where Y is nothing but G plus JB, where B is nothing but BC minus BL. So G nothing but 1 by R, BC nothing but omega C, BL nothing but 1 by omega L, and the phase difference is phi is equal to tan inverse of BC minus BL by G, and the power factor is cos phi, and average power is Vrms Irms cos phi. Therefore, for parallel RLC circuit, if BL greater than BC, current lags the voltage by phi, and the circuit behaves like inductive. And for the case BL less than BC, current leads the voltage by phi, and the circuit behaves like capacitive. Next, we will see some different types of powers here. So we have 3 types of powers actually. So real power, reactive power, apparent power. Okay, so we have other names for real power. It is also called as active power, true power, useful power, average power. So it is given by P is equal to Vrms Irms cos phi. Its units are watts or kilowatts. Next, reactive power or imaginary power. It is given with Q, Vrms Irms into sin phi. Its units are VARS, volt ampere reactives, or kilo volt ampere reactives. Next, apparent power. So apparent power is the absolute value of the complex power. Therefore, so it is mod S. So nothing but root over P square plus Q square, that is given as Vrms into Irms. Its units are voltage into current, that's why volt ampere. So the complex power is nothing but complex sum of the real and reactive powers. Therefore, S is equal to P plus JQ. So the modulus of this S is nothing but apparent power. So next, power factor is given as cos phi. So it is a ratio of active power to the apparent power. So from power triangle we can write here. So here, so phi is nothing but power factor angle. On the adjacent side we have real power, this is a reactive power, and this is a apparent power. Therefore, cos phi is equal to P by S, that is active power to the apparent power. So from impedance triangle here, Z is equal to R plus JX. So R is nothing but adjacent side, X is nothing but opposite side, Z is the hypotenuse. Therefore, if you apply cos phi, so cos phi is equal to R by Z. So therefore, these are the some important formulas from Unit 2. We will see the important formulas from Unit 3 in the next video. Thank you.